We have seen a brief introduction regarding the normal modes of continuous systems in our previous lecture. Now, as a first example, we will see how we can find the normal modes of vibration of a string. In fact, I have told you that a string is a very good example or a very practical example for a continuous system, and it finds its application in so many musical instruments like violin, like sitar, guitar, and so on. Okay. So the problem of vibration of a string is the most important problem for in case of the waves and oscillation. Okay. And here, first of all, we will see how a string vibrates when it is plucked in a direction just perpendicular to its length. This is called transverse vibration. Okay. And for this we consider a uniform string, also a homogeneous string you can say, and let us say this string is lying along the x-axis and it is stressed under a tension. As you can see in this figure, I have shown that here T is the tension, this T is tension, and so the string lying along the x-axis is subjected to a tension T. Okay, so it is called a stressed string. Okay, and in this figure I have shown actually a segment of this string, this AB, which I have shown by a deep line. You can see this actually represents the segment of our string. Okay, and as you can see in this figure, I have assumed that the x coordinate of this point A is x1 and that of point B is x2. So the length of this segment AB of the string is x2 minus x1, which I have represented by the symbol delta x. Okay. Actually, when no disturbing force, no perturbing force has been applied on the string, then it lies along the x-axis. Now let us consider that this segment of a string is plucked by applying a transverse force, that is a force is applied in y direction, since the string is lying in x direction, and when you will actually apply this apply a force in y direction, then this segment AB of the string get displaced slightly, but we apply a force such that the displacement of this segment is very small, so that it will execute a small oscillation. Okay, and as you can see in this figure, I have shown that this A dashed B dashed, this is the displaced position of this segment of the string. Okay, actually in general you can say that at the displaced position the string will not remain almost straight, but in general when the element is displaced along the y-axis to a new position A dash B dash, this element is no longer exactly straight, but it has a slight curvature and the tension is tangential to the curve, as you can see. Here at the end A dash, you can see tension is T, which is tangential to this curve A dash B dash at point A dash, and at B again you can see that tension is T, which is tangential to this curve. Okay, and I have shown that this tangent makes an angle theta 1 with x-axis, and here the tension T makes an angle theta 2 with x-axis. Okay, Actually, due to if you make the displacement, let us say y, and this y is not very large, then the tension T in this undisturbed state and at this disturbed state will remain almost constant. And if the spring is not very heavier, tension throughout it is same. And in this calculation, you will also see that we will make an approximation that this delta x tends to 0, so that this element AB just behaves like a infinitesimal element, or you can say just as a particle. Okay. Now, displacement of any point of this segment actually depends on two variables. First one is x, it means the position coordinate, and another is time. So in general, you can say that the transverse displacement, this y, is a function of x and t. Okay. So y of xt be the transverse displacement of this element located at point x and time t. Okay. Actually, after plucking, when the string is released, the displacement of the element will change with time. And so you can say that displacement is a function of both x and t. X and t. So I have written x comma t in the argument of y. Okay. Now actually, finding the resultant force on this segment A dash B dash at its displaced position, we will actually write its equation of motion on the basis of Newton's second law of motion. And writing this, you can find what will be the equation of motion of this element. And for this, you can see, if you will resolve the tension T acting at point A dash, its x component, you can see the figure, this will be t cos theta 1, and its y component will be t sin theta 1, and it will be actually in the negative y direction. Okay. And actually, in the similar manner, you can see here, when you will resolve this tension T acting at point B dash, its x component will be t cos theta 2. This t cos theta 2 is in positive x direction, while this t cos theta 1 was in negative x direction. And the y component, or the vertical component, you can say, of this t will be t sin theta 2. Okay. Now, neglecting the effect of gravity on this string because it is not very heavier, you can find the net force acting on this element in x and y direction. In x direction and y direction, we can easily find the net force. See this figure. And you can see, if we make a free body diagram, let us say this point represents the element AB or A dash B dash. Then you have seen that in positive x direction, this element experiences the force T cos theta 2, and in negative x direction, it experiences the force T cos theta 1. You can see this figure. This T cos theta 1 is along the negative x direction, and T cos theta 2 is along the positive x direction. Okay? And similarly, in positive y direction, you have seen the tension acting on this element is T sin theta 2, and in negative y direction, this is T sin theta 1. Okay? So if you will consider that this Fx is the net force acting on this element in x direction, what will be its value? It is obvious from this free body diagram that this Fx, which is the net force acting on the element in x direction, that will be simply equal to t times cos theta 2 minus cos theta 1. Okay? Or you can say t cos theta 2 minus t cos theta 1. I have taken this t as a common factor. And the net force acting on this element in y direction, that will be t sin theta 2 minus t sin theta 1. And I have taken here this t as a common factor. Okay. Now, as I have told you earlier, that our aim is to displace this string by a little amount, because we are seeing a small oscillation. Okay. So, in case of a small oscillation, this displacement y of xt will be very small. Okay. And if y of xt is very small, in that condition, the angle theta 1 and theta 2, which you know are the angle made by the tensions or the tangents to the curve with the x and y x-axis. Okay. So when this displacement will be very small, the curvature of the string will be very small. Okay. And in that condition, both of these angle theta 1 and theta 2 will be also very small. Okay. And mathematically, you may say that both theta 1 and theta 2 in case of very smaller value of y will tend toward 0. So let us analyze our result in this limiting condition. And you know from from the limit theory that if theta 1 and theta 2 are very small, then cos theta 1 is almost equal to 1. You know, limit theta tends to 0, cos theta is equal to 1. Okay. And in this condition, sin theta and tan theta, you know, both are equal when theta is very small. And that is simply equal to theta. So you can say that sin theta 1 is equal to tan theta 1 and sin theta 2 is equal to tan theta 2. Okay. So in this limiting condition, what will be the value of this fx? You can check. Since under this condition, both cos theta 2 and cos theta are equal to 1. So this fx will be t times 1 minus 1, it means 0. So resultant force acting on this element in this horizontal direction, or you can say in x direction, is 0. Okay. But our string experiences a resultant force in y direction. And what is that force? You can see Fy is given as t times sin theta 2 minus sin theta 1. But in this limiting condition, you have seen that sin theta 2 can be replaced by tan theta 2 and sin theta 1 by tan theta 1. Because theta 1 and theta 2 are very small. And in this limiting condition, sin theta and tan theta are equal. And you know from geometrical meaning of derivative that this tan theta is actually the slope of the curve. And in calculus you have studied that slope of this curve is simply equal to derivative of y with respect to x, dy by dx. So this tan theta 2 is the slope of the curve at point B dash, and that will be geometrically equal to del y by del x at x equal to x2. Okay. And similarly, this tan theta 1 will be equal to del y by del x at x equal to x1. Mark here, why I have written del y by del x, that is partial derivative, not dy by dx, not the total derivative. Why I have written so? Because you know our function y is a function of two variables x and t, not only of x. So if you will find its derivative with respect to x, you must perform the partial derivative, keeping this t as constant. That's why instead of dy by dx here, I have written del y by del x. Okay? I think you clearly understand this point. Okay? Now let us consider that this del y by del x at point x equal to x2 is equal to f of x2, and del y by del x at x equal to x1 is equal to f of x1. I have assumed it. Okay. Here actually this del y by del x have been written equal to f of x. Okay. And therefore f of x2 has been written instead of del y by del x at x equal to x2, and f of x1 has been written instead of del y by del x at x equal to x1. Okay? And therefore, now our aim is to find this Fy for writing the equation of motion, and for getting the value of Fy, you must have to find the value of this f of x2 minus f of x1. And for this, we will see the Taylor series or Taylor's expansion. I hope you have definitely studied Taylor series. If you have not studied it, you can watch my videos in mathematical physics on Taylor series. You know from Taylor series that this f of x2 is given as f of x1 plus x2 minus x1 times del f by del x at x equal to x1 plus 1 over 2 x2 minus x1 whole square times del 2f by del x square at x equal to x1 plus so on. The third term is 1 by 3 x2 minus x1 whole cube del 3f by del x cube at x equal to x and so on. Okay. Now as you have seen in the figure, I have assumed that this x2 minus x1 is equal to delta x. So instead of x2 minus x1, I have written delta x at both places. Okay. Now, if you treat the string to be made up of very small elements, so in this condition, we must think that this element, although shown in the figure, is larger, but our assumption is this AB is very small. When AB, which is the element of the string, will be very small, it means this length delta x of this element will tend to 0. This is very small. And you know, if delta x is very small, it tends to 0, then delta x square, delta x cube, delta x to the power 4, all these delta x containing higher powers will be negligibly small. So in this limiting condition, when you assume that the element is very small, or you simply say that delta x tends to 0, you can neglect all the terms containing higher powers of delta x. And so in this first order approximation, we will neglect the term containing delta x squared, delta x cube and so on. And therefore, you can see this f of x2 then becomes f of x1 plus delta x times del f by del x at x equal to x1. Okay? And when you will bring this f of x1 in LHS, your equation becomes f of x2 minus f of x1 is equal to delta x del x del y by del x. Because you can see, what is this f of x1. This is del y by del x at x equal to x1. So instead of f, you may write del y by del x. Okay. So here f has been replaced by del y by del x, and it is understood that we are talking about x equal to x1. Okay. So this is equal to delta x times del 2y by del x square. Okay, del 2y by del x square. But you know, y is a function of x and t, so for its specification, you can say that f of x2 minus f of x1 is equal to delta x times del 2y of xt by del x square. Okay. So in this way, applying the Taylor series, we have obtained the value of this factor f of x2 minus f of x1. Now after getting its value, let us substitute it in this equation number 1 for getting the value of fy. So when you will substitute this value in equation 1, you will get fy. And you can see fy will be then t times delta x times del 2y of xt by del x square. Okay. So in this way, what is the net force acting on this element in y direction we have obtained. Okay. Actually, the equation of motion of the element is to be obtained. This is our aim. And this is obtained from the Newton's second law of motion. And you know from Newton's second law of motion that force is equal to mass times acceleration. Okay. So now on the basis of Newton's second law of motion, we will try to find this fy. Okay. And for this, we consider that this mu is the linear mass density of our string. When you say linear mass density, what does it mean? It means it is the mass of the string per unit length. As you know, we have assumed earlier that our string is uniform. So, mass per unit length at everywhere will be same. So, mu will have a constant value. If the string will be non-uniform, its cross section changes point to point, then mu will be not a constant. Here, if total length of the string is L and its total mass is m, then mass of unit length will be m by L, and this m by L has been written as mu. This is called linear mass density or mass per unit length. Okay. So, can you say what will be the mass of this element AB? As you know, mass length of this element is delta x. And you can see mass of unit length is mu. Therefore, mass of delta x length will be what? That will be mu into delta x. So, this is the mass of the element. Okay. And if you treat this element just as a point for showing its free body diagram, then you know it suffers a displacement y of xt in y direction. So what will be its acceleration? You know, when you will differentiate this y 2 times with respect to t, then you will get actually the acceleration of this element. So now we can find the value of Fy on the basis of Newton's second law of motion, which states that it will be equal to mass of the element. I have assumed that this delta m is the mass of the element. Delta m is what? This is mass of this element. And Ay is its acceleration in y direction. But as I have shown just now, that this mass of the element will be simply equal to mu times delta x. And acceleration, this will be second order derivative of y with respect to t. But again mark it, y is not a function of t only, it is also a function of x. So you must take the partial derivative. Okay, you must take partial derivative because y is also a function of. So I have not written d2y by dt square, not ordinary derivative, but I have written the partial derivative del 2y of xt by del t square. This is acceleration. So in this way, we have obtained the value of Fy by applying Newton's second law of motion. Now, you can write the equation of motion of this element. Force acting on this element in y direction is Fy, which is equal to this much, and you have already obtained that this Fy is equal to this much in this equation 4. So now, let us substitute this value of Fy in equation 4 for writing the equation of motion of this element. And so you can write mu times delta x times del 2y of xt by del t square is equal to t times delta x times del 2y of xt by del x square. Okay? I think you have clearly understand each and every step. This is just a simple concept. Now you can see this delta x is present in both sides, so that will cancel out. Okay, and therefore del 2y by del t square is equal to t over mu times del 2y by del x square. Okay, del 2y by del x square. Actually, here t and mu both are constant when the string will be homogeneous and uniform. And I have written v square at the place of t by mu. Or you can say that I have written v instead of a square root of t by mu. Why this symbol v has been used? Actually, when you will find the dimensions of this t by mu, dimensions of t means dimensions of force, and dimension of mu will be what? This is mass per unit length, so this is ml inverse. Okay, and dimension of t will be ml t inverse 2 and divided by ml inverse. M will cancel out, and you can see this will be L square t inverse 2. Okay, this is the dimension of t by mu. So when you will take its square root, this will be Lt inverse, which is dimensions of velocity. So this symbol has been used. Actually, this quantity square root of t by mu has dimensions of velocity. Okay. When you study the wave motion, I have already provided videos on wave equation earlier, and you can see my playlist on waves and oscillation and watch that video. When you will watch, you will find there that this equation defined in equation number 6 is the well-known classical wave equation. And when you say that this equation represents a classical wave, then this v represents the phase velocity or the wave velocity of the wave. But here we are not dealing the problem of wave. After this chapter, we will start again dealing the problem of wave. Okay? So here I will not say that this v is the velocity of the wave. But actually, when this string will vibrate, a transverse wave is generated on the string, and that transverse wave travels with this speed v, which is equal to a square root of t by mu on the string. Okay? But that wave propagation we will discuss in our next chapter. Okay? Here our aim is not to discuss the wave aspect of this problem, but the result will remain same. Okay? So here we will only treat this v just as a constant factor or just as a quantity whose dimension is equal to dimension of velocity. Okay. So so far we have not explicitly stated that this v is the velocity of the wave. This is the subject matter of our next chapter. Okay. So for the time being, however, all that we can say that this v is a constant having dimension of velocity. Okay. So this is a most important result, and when a question will be asked in short answer type, derive expression for transverse wave traveling on a stressed string, this will be the expression. Okay. But this is one of the parts of our problem. The basic problem is to find the normal modes of vibration of this string. Okay. So now let us try to find the normal modes and normal mode frequencies and shape of modes of this vibrating string in case of vibrating string. Okay. And for this, let us consider the string in our consideration is rigidly fixed at 2 points. One point has been taken at the origin, x equal to 0, and if you consider that the string is of length L, then it is rigidly fixed at its another end. Okay? Its another end. That is, let us say at point P. So at point O, or x equal to 0 and x equal to L, the string is rigidly fixed, clamped. Okay. Now let us apply a force, let us say F, in the transverse direction, that is in y direction. The string is lying along x-axis, and it is also stressed. You have to suppose that there is a string, there is a tension T which stretches the string. Okay. Now a small jerk is applied in the y direction, that is along a direction perpendicular to the length of the string, and the string is released. When you will plug the string in transverse direction and release the string starts vibrating. Okay, the string starts vibrating due to its elastic property. Okay, and so in order to find the normal modes, we assume the existence of a normal mode of frequency omega, okay, and phase constant, let us say phi. Okay. This means that every particle of the string will execute simple harmonic motion of angular frequency omega and phase constant phi. Okay. And if the string is executing, every particle of the string is executing SHM, then for the normal mode, you can write the displacement y of xt in this manner. You have already studied in my lectures on SHM. This will be A times cosine of omega t plus phi. Here I have written A of x because here amplitude will be not constant. For different points or for different particles, this amplitude will vary. It depends on x. So in this condition, you must write A of x, which represents that A is x dependent. Okay. Actually, these are infinite number of equations, one for each particle, characterized by its x value in the range of x barabar 0 to x barabar L. Okay. Actually, the variable y of xt, which you are seeing in this equation 8, is the displacement at time t of a particle located at a point, let us say x. This is x equal to x, and its displacement has been shown by y of xt. Okay. And ax, as I have told you, this is the amplitude of its motion, which is also x dependent. Okay. In fact, the amplitudes of all particles of the string will determine the shape or the configuration of the mode, which we will discuss later on in this video. Now, for getting the normal modes and normal frequencies of vibration, Let us say do some mathematics here. First of all, you can see y is a function of x and t. Now our aim is to find the second order derivative of this y with respect to x and also with respect to t. Why we are doing such a calculation? Because you can see this equation 6. This equation 6 contains the second order partial derivative of y with respect to t and also with respect to x. So now let us try to find those two derivatives from this equation 8, which we have written for a particular mode of vibration. See this equation. When you will find del y by del x, it means you have to keep t as a constant. So keeping t constant, this will be equal to dA by dx times cosine of cos omega t plus phi. But you have to find the second order derivative. So again differentiate it with respect to x partially. So del 2y by del x square, this will be d2a by dx square times cosine of omega t plus phi. Okay. Now in the similar manner, when you will differentiate this y with respect to t partially 2 times, your result will be minus omega square times a of x times cosine of omega t plus phi. Okay. Now these two values, that is the values of del 2y by del x square and del 2y by del t square, which we have obtained here. Now let us substitute these two values in this equation 6, which I have written earlier. Okay. So after substituting these two values in equation 6, your result will be minus omega square times a of x times cosine of omega t plus phi equal to v square times this much. Okay. Now you can see this cos omega t plus phi and cos omega t plus phi present in both LHS and RHS will cancel out, and our result becomes d2a by dx square equal to minus omega square by v square times ax. Okay. Or you can write this equation as d2ax by dx square plus k square times ax equal to 0, where k has been written instead of omega over v. Omega over v. For omega over v, I have written here actually k. Actually, the parameter k will be identified to be wave number or wave vector of a wave when we will discuss the wave theory. Then you will see that actually this omega over v, which is represented by the symbol k, that is a well-known quantity, a well-known characteristic of a wave, which is called wave vector or wave number. Okay. But as I have told you earlier, the aim of the present lecture is not to deal with the problem of wave. We are only considering vibration, not wave. So here I will not tell you to say this k as wave vector, because we are not talking about wave. Here we will only say that this k just stands for omega by v. This is a constant, and here v is equal to this much. Only this will say. Actually, this equation 9, which you can see here, actually this equation governs the shape of the mode. You will see this fact some time later. And when you will compare this equation 9 with the well-known equation of SHM, d2x by dt square plus omega square x equal to 0. This is the well-known differential equation of SHM. You can see equation 9 has the same form as that of the equation of SHM. So definitely this equation 9 will also represent some oscillatory motion. Here the quantity Ax is oscillating instead of x. In this case, x oscillates with t. But here Ax oscillates with x. So you can say that this is the familiar differential equation of SHM, except that it represents oscillation in space rather than in time. It is not oscillation in time, t, but it is oscillation in space. And which quantity is oscillating? The quantity which is oscillating is A, not x. Okay? And so, on the basis of the idea which we have discussed in the solution of equation of SHM, now you can easily say what will be the most general solution of this equation 9. You know, the most general solution of equation of SHM is a linear combination of its sine solution and cosine solution. You have already studied. So the most general solution of this equation is given as A of x equal to c times sine kx plus d times cos k. Here, you know, c and d are unknown constant. Actually, these are the two integration constant. You can see this is a second order differential equation. So actually, when we will want to solve it, we have to integrate this equation 2 times. And during those two integration, we will have two integration constants. So actually, c and d are those two integration constants. Okay. So now, as Ax has been defined like this, and therefore now the general solution for the displacement y of xt, now you can write in easy manner. You have seen that y of xt is given by this expression, a of x times cosine of omega t plus pi. But you have defined this a of x in this manner, so y of xt is given as c times sine kx plus d times cos kx times cosine of omega t plus pi. Okay? But you know, this c, d are not known. So applying the appropriate boundary condition, we can obtain the values of c and d. And what will be those boundary conditions? You can easily understand. You have seen that our assumption is the string under consideration, whose length is L, is rigidly fixed at point x equal to 0 and x equal to L. So when this string will vibrate or it will be plucked, does point x equal to 0 and x equal to L will get displaced? Answer is no, because it is rigidly fixed. So point x equal to 0 and x equal to L will never get displaced. And therefore, y, which is displacement of any point of this string, will be always 0. At all time it will be 0 at these 2 points. So these are the two important boundary conditions applying which we can find the values of the arbitrary constants c and d. So let us see, I have written the first boundary condition is y is equal to 0 at x equal to 0. In other words, you can also write it in this manner, y at 0 comma t is equal to 0. Here 0 has been written at the place of x. And the second condition is y is equal to 0 at x equal to L. X equal to L. Okay. Or in another manner, you can write y at L comma t is equal to 0. Now let us apply this first boundary condition on this equation 11 to get the value of these constants. So when you will apply this first condition on this equation 11, you can see in RHS where there is x, we will substitute 0. And in LHS, you can see when x is 0, then according to the first boundary condition, this y is 0. So 0 will be equal to c sine 0 plus d cos 0 times this much. But you know sine 0 is 0. So this first term in RHS will vanish. And cos 0 is 1. So d cos kx will be simply d. Okay. So you can see after application of this condition, our result will be 0 equal to d times cosine of omega t plus phi. But you know, can this cos omega t plus phi will be 0 at all time? No. At a particular time, at a particular value of t, it is possible that cosine of omega t plus phi may be 0. But one cannot say that all time t this cosine will be 0. But in RHS there is 0 at all time. So definitely the other factor d must be equal to 0. Because cosine of omega t plus phi may or may not be 0. So for the validity of this result, this d must be equal to 0. So in this way, we have obtained the value of one of the constant d. After getting the value of d, now you can write this expression, which I have defined in 11, taking d as equal to 0. So when you will take d equal to 0, what will be this y of xt? This will be c sine kx times cosine of omega t plus phi. So y of xt is now given as c times sine kx times cosine of cos omega t plus phi. Okay. Actually, when we will discuss the standing wave on a string in our forthcoming lectures, then you will see actually this equation defined in equation 12 is nothing. This is simply the equation of a standing wave. But here I have told you earlier that our aim is not to discuss the wave traveling on this string. Only our aim is to discuss its mode of vibration. Okay. But later on we will see that this equation is actually equation of a standing wave. Okay, one-dimensional standing wave. Now, after when we will apply now the second boundary condition, then we can see we will get the frequencies of this vibration of this string, which is called normal mode frequency. For getting the value of normal mode frequencies, or you can say that the frequencies of the normal modes of transverse vibration of the string can be obtained by using the second boundary condition. And what is the second boundary condition? You know, second boundary condition says y is equal to 0 at x equal to L. Okay. So now let us put in equation 12 y equal to 0 and x equal to L in RHS. So you can see this equation 12 now becomes, after the application of this boundary condition, 0 equal to c times cos sine kl times cosine of omega t plus phi. Again, you know, for all t, cosine of omega t plus phi cannot be 0. So definitely this c times sine kl will be 0. But this c can also not be 0, because you can see if c is 0, see equation number 12, then this y of xt will be 0 at all t. It means the string is never displaced. Is it correct? It is completely incorrect, because we are plucking the string and it get displaced. So C can't be 0. Okay? I think you have clearly understand what I am telling you, because if you will choose that C is 0, then this equation will get satisfied. But you can't take c equal to 0 because for this c equal to 0 correspond to a trivial solution of a string permanently at rest. It never get displaced because y will remain 0 at all time t. Okay? So hence we have to take sin kl equal to 0 because this c cannot be 0. Now, when sin kl is equal to 0, you know the general value of kl will be equal to n pi, and therefore k will be equal to n pi over l. Here, n has values 1, 2, 3, 4 and so on. But you know, mathematically, when n is equal to 0, then kl will be 0 and this equation will get satisfied. Mathematically that is all right, but physically it is not possible. Here in this physical condition, it is not possible. Why it is not possible? Because when you will take n equal to 0, you can see that this L will be equal to 0. It means there is no string. Okay, there is no string. Or you can say that in this is completely unphysical. So you can't take n equal to 0. Okay, we can take n equal to 1, 2, 3, 4 and so on. Okay? And therefore I have written n is equal to this much. So here k will be equal to n pi over l. Okay, but you have seen earlier that this k is equal to omega over v. Here for different value of n, k will have different value, and therefore I have written it not omega by v but omega n over v. This is for nth mode. Okay. But you know omega is equal to 2 pi nu, where nu is the regular frequency, you know, frequency measured in hertz. So omega n is written as 2 pi mu n, and that is equal to n pi over l times v, and therefore this nu n is equal to n over 12 times v. This is a most important result when we will discuss actually the laws of transverse vibration of a string. Then we will write this expression directly. Okay. But you have seen that this v is equal to a square root of t over mu. So nu n is given as n over 12 times a square root of t over mu. So this is the general expression for the different frequencies for the different mode of vibration. Now you can see, if your aim is to find the least value of frequency, you have to take the least value of n, and you know least value of n is 1. Okay, and when we will take n equal to 1, then we will get the smallest or the least possible frequency of vibration of this string. Actually that least frequency of vibration of a string is called fundamental frequency, and the mode of vibration of the string in that condition is called fundamental mode. So when the string will vibrate in its fundamental mode, in its lowest mode, the frequency is given by nu1 equal to 1 over 12 times a square root of t over v. Now you can see, when you will find the higher modes of frequency, for that you will take n equal to 2, 3, 4. Actually these are called the overtones. This new one, this is the fundamental frequency, and when you will take n equal to 2, 3, 4 and so on, those frequencies are called overtones. Or you can say when n is equal to 2, that is called second harmonic or first overtone. In terms of harmonic, n equal to 2 will represent second harmonic, okay, or first overtone. Similarly, n equal to 3, this will represent third harmonic or second overtone. Okay, and you can see the second harmonic or first overtone is just 2 times of the fundamental frequency. The third harmonic or the second overtone is 3 times of the fundamental frequency, and so on. Okay? So in this way you can find the normal mode frequencies. Okay, and I think the calculation is very simple, and definitely you can understand it in a very simple manner. So from this result you can conclude that a string has an infinite number of possible frequencies of vibration, which are harmonics of the fundamental frequency nu1. Actually, the fact that the mode of frequencies nu2, nu3, nu4, etc. are harmonics of fundamental mode frequency nu1 is a result of our assumption that the string is perfectly uniform and flexible. This result will be possible only when your assumption is your string is perfectly uniform and perfectly homogeneous, perfectly flexible. The tension is throughout same. Only then this result is possible. But in case of actual strings, real strings, these results do not strictly are found. Okay? Why these results will be not obtained strictly in practice? Because the reason is that the strings in a real physical system such as strings of violin or piano or guitar or sitar are not perfectly uniform and flexible. Okay? So these are actually the theoretical result. Okay? Now we will see the last aspect of this problem. This is regarding the normal mode shapes. What will be the shape of the normal mode of vibration of this string? Let us see. Actually, this shape is obtained by the displacement equation. You have seen that the displacement equation of the vibration of this string is given as y of xt equal to c times sine kx times cosine of this much. Okay. Now for different mode, this y will have different value. So let us think about nth mode of vibration. And for nth mode, we write y as yn, c as cn, and k as kn, omega as omega n. So I have made these changes. Now if you want to find the shape of the fundamental mode, then you must take n equal to 1, because you know for fundamental mode vibration n is equal to 1, and therefore this equation 15 for fundamental mode can be written as y1 of xt equal to c1 times sine k1x times cosine of omega 1t plus pi. Okay? But you know what is this k? You have seen that k is equal to n pi x over L. K, I have defined n pi by L, not x. K is equal to n pi by L. Okay? N pi by L. So when n will be 1, k1 will be equal to pi over L. So here, at the place of k1, we will write pi over L. So y1 of xt becomes like this. Now you can see, this y1, you know, is 0 at x equal to 0 and x equal to L. It is well known because our string is rigidly fixed at these 2 points. So y is always 0 at these 2 points at all time t. But except this point x equal to 0 and x equal to L, at any point between x equal to 0 and x equal to L, you can see this equation, this y cannot be 0. And when x is equal to L by 2, take here x equal to L by 2, then this will be sine pi by 2, which is maximum, which is 1, which is its maximum value. So at this point where x will be equal to L by 2, at this point this y is maximum. Actually this point is called antinode, okay? Where the displacement is maximum, that point is called antinode. And the point where displacement is permanently 0, that is called node. So in this case you can see there are two nodes. First node is at x equal to 0 and another is at x equal to L. And there is only one antinode at x equal to L by 2. So x equal to L by 2. And so the shape of this fundamental mode will be as shown in this figure. Now actually the region between two successive nodes is called a loop. So here there is a node at x equal to 0 and x equal to L. So this region between x equal to 0 and x equal to L is called a loop. So in fundamental mode, our string vibrates in only one loop. So you can see I have marked these important facts here. In this case, number of loops is 1, number of anti-nodes is 1, and number of nodes is 2. You will always see that the number of loops and number of anti-nodes in this case will be equal, and number of nodes will be greater, larger than this number of loops or anti-nodes by 1. You will always see. Now we are talking about the first overtone or the second harmonic. You know, for first overtone or second harmonic n is equal to 2, and therefore in this case displacement y2 of xt is given as c2 times 2 pi x over L times this much. Now see this equation. As you know, since a string is clamped at its two ends, so it is well known that y is 0 at x equal to 0 and x equal to L. It is well known. Okay? But from this equation, when you will take x equal to L by 2, then let us see this sine 2 pi x over L. This will be sine 2 pi over L into L by 2. L and this 2 will cancel. This is sine pi, and this sine pi will be equal to 0. So at this point x equal to L by 2, again this y2 will be 0. Therefore, there will be a node just between these 2 points, x equal to 0 and x equal to L. At this point x equal to L by 2, displacement is permanently 0. Although this point is not clamped. Point at this n1 and point at n3 are permanently clamped, so that they are permanently at rest. But this point n2 is not clamped, but it remains permanently at rest. This is the nodal point. Okay? And so you can see in this condition there will, and again when you will put x equal to L by 4 and x equal to 3L by 4, then you will see that this sine function will be maximum and y2 will be maximum. So these points at x equal to L by 4 and x equal to 3L by 4, where y2 is maximum, these are antinodes. Okay? So in this case, in case of first overtone or second harmonic, you can see our string vibrates in two loops. There are two antinodes and three nodes at n1, n2 and n3. Antinodes are at a1, a2 and a2, where x is L by 4 and 3L by 4. Actually, in this manner, you can obtain the shape of the higher modes of vibration of this string. Okay. So, I think the problem of transverse vibration of a string is now completed, and definitely you have enjoyed this video. Thank you very much.